Alright, so let's talk about how closures work. So, let's see here. So, for part A, what we want to do is here. So, let's write out. So, a prime let a prime be the set of limit points of A. Note that then we have the closure of A is just the union of A with the set of limit points of A. Alright, so what are we trying to prove? I think that, I guess introducing the BNs makes the notation a little bit nicer. But the way that I like to write it is like this. So the union from I equals 1 to n of AI closure equals the union from I equals 1 to n of AI. But you take the closure over each individual AI. So what we're trying to prove is that the closure of the union is equal to the union of the closures. So we've actually done part of this exercise in a previous exercise, but let's go through the details. So, see here. First, let x be in the union from 1 to n of AI. This is a little bit shorter notation. I guess I'll write I equals 1 to n of AI just to be super clear on what I'm doing. But sometimes people will, instead of writing I equals 1 to n, they'll just write 1 to n. And then the only thing that you see the only thing you see in here that is typically ever used as an index is lowercase I. So you know, oh, well, this union here is really from I equals 1 to n. And so you can sort of use, if you just write union from 1 to n, you could sort of take what you're looking at and sort of automatically know, oh, I guess we're doing the union from I equals 1 to n. Because that's the only thing that would make sense. But in any case, at this point, it probably makes more sense to be really explicit in notation. So we take any x which is in the union of the closures. We want to prove that it is in the closure of the unions. If x, let's see here, then, well, if x is in the union of the AIs, then there must be some index j such that x is in the closure of AJ. So x is in the closure of AJ, so x is in AJ, or x is a limit point of AJ. If x is in AJ, then obviously x is in if it's in AJ, then it's also in the union from I equals 1 to n of AI, because AJ is completely here. So then x is in AJ, which is contained in the union from I equals 1 to n of AI, which is obviously contained in the union from I equals 1 to n of AI, this entire thing closure. Okay, and that's what we're trying to get at. So in the case of x being in AJ, we're good. Otherwise, or I guess we can say if x is a limit point of AJ, then there exists a sequence xn which is contained in AJ, but which it's contained in the elements. It's contained in the set of elements of AJ not being equal to x, such that xn goes to x. That's what it means to be a limit point. Right. Okay. So now, the sequence xn, well, this is contained in aj, and it's not in x. But aj is contained in the union of the aj's. So this is contained in the union from I equals 1 to n of aj. And again, we're still removing x from the set. Okay. So xn is a sequence of elements in this union not being equal to x, such that the sequence converges to x. But that implies that x, the existence of such a sequence being in this union and converging to x, means that x is in the closure of the union. So x is in the union from I equals 1 to n of aj, and then we take the closure. No, this should be the union of ai. That should also be the union of ai. I don't know what I'm doing. I need more coffee. Alright, so, yeah. Hence, the union from I equals 1 to n of ai closure is contained in the union from I equals 1 to n of ai in the closure of that entire thing. Okay, yeah, so always remember, when we're trying to prove the inequality of sets, we want to show that each set is contained in the other. I know when I was first starting with analysis, whenever I would see one of these things, I would want to be like I'd want to do it like straightforward, like start at this set, start at the first set, make that equal to something, and make that equal to something, and make that equal to something, and then keep going, and eventually get to the thing that I want. And a lot of times you're either not able to do that, or it's quicker to do both directions. And it is sort of tempting, like you can sort of trick yourself into thinking, oh, well, if I can just do a bunch of, like a string of equalities, then surely that'll be quicker than having to do one inclusion and then another inclusion. Because if you're doing two separate inclusions, then you're doing two things. And if you're just showing equality, you're just showing one thing. But it ends up taking you extra time because it won't work, and you'll just be banging your head against a wall trying to figure out how to do the proof. So whenever you see an equality of sets, just even if you don't want to, you really should try just doing by inclusion, and it will usually work, especially for these types of exercises. Okay, so anyways, we've done one inclusion, and now we do the other one. So for the reverse inclusion, let x be in the union from I equals 1 to n of ai, the closure of this entire thing. If x happens to be in the union from I equals 1 to n of ai, then x is in ai. Well, I'll write this as aj. I'll use I for indexing and j for like a particular index. Then x is in aj for some j, and of course j is between 1 and n. And so, in this scenario, we have x is in aj, which is contained in aj closure, which is contained in the union from I equals 1 to n of ai closure. And that's the thing that we want x, that's a set that we want x to be in, and so we're good here. If x is not in this union, but in, or if all we know about x is that it is a limit point of this union, then what does this mean? For it to be a limit point, then there needs to be a sequence of x in union from I equals 1 to n of ai, and we remove x, such that xn converges to x. And now when I say this, I guess just going back to the definitions, like if you wanted to do this like as low level as possible, you would want to go back to the definitions, and instead of saying like this is a little bit of a shorthand notation, because what you would want to say is that for every neighbor, not necessarily that there is a sequence contained in this set which converges to x, but rather that for every neighborhood of x, there is a point in that neighborhood and in this union which is not equal to x. Wait, there is a point. You'd want to say that for every neighborhood every neighborhood n of x, there exists a point y which is in n, and it's also in the union from I equals 1 to n of ai, but it's not equal to x. So I guess looking at going back to the definitions, this if you wanted to talk in terms of neighborhoods, this is what you would want to write out. I think this is definitely something that you want to be really useful with working with, but if you're just as comfortable working without introducing this neighborhood n here, then what I've written up here saves a lot of notation. And I also like to talk in terms of having sequences which converge. I sort of just prefer having that. So it's just a personal preference that I choose this. So anyways, we have a sequence which converges to x. A sequence in this union of elements not equal to x, which converges to x. Okay, so this sequence belongs to this union of the AIs, and now we're going to use a trick that I introduced in one of my other videos. So let ij be the set of indices, let's say m in the natural numbers. Again, this set does not include 0. This is a set of indices such that xm is in aj. And this is, of course, for j between 1 and n. Oh, I guess this is sort of... I've been using n in multiple different ways. M, n. So let's call this k and n such that xk is in aj for j between 1 and n. And I guess these sequences we'll index these sequences by m. It's just nice to be using different letters for different things. Sometimes it can get confusing if you're reusing a lot of letters. But sometimes, like in this case, if you don't want to reuse letters at all, then you sort of run out of letters, which is not good. If you're able to sort of look at this sequence of, and then you have xm and xn in brackets, and then you see, oh, that's just any sequence, and that n that appears in there is not at all related to the n that we're using to refer to the number of sets. Then if you just sort of get used to that, to automatically not being too fussy about reusing letters, then it can make a lot of your notation nicer. It just depends. Okay, so let ij be the set of indices such that xk is in aj, and this is for each of these. Then every single xm is contained in this union, so every single xi is contained in some aj, which means that the union from j equals 1 to n of ij must be all of n. Because obviously the union of the ij's is a union of sets of natural numbers, and so it's contained in the natural numbers. And every single natural number is contained in some ij by what I just was talking about. And so you have equality of these two sets. Okay, so anyways, these sets are equal. And the set on the right is infinite. Okay, I guess I should make these i's because I'm using this as an index. I know I is not great, but whatever. So, ij is infinite for some j. So, what are we going to do? We're going to call these mk from k equals 1 to infinity. This is going to be ij. So ij contains infinitely many natural numbers, and you order them from smallest to greatest, and you label them as mk. So m1 will be the first element of ij, m2 will be the second element of ij, m3 will be the third element of ij, and so on and so forth. Then, the sequence consisting of xmk, where k ranges from 1 to infinity, well, because each mk belongs to ij, each xmk belongs to aj, and so this is in aj. And furthermore, xmk converges to x as k goes to infinity, and that's because xm converges to x as m goes to infinity, and so that convergence will remain true if you let the if you restrict it to a subset of indices. Okay? Thus, what does this tell us? Well, then we have a sequence in aj which converges to x, which means that x is in the closure of aj, which is contained in the union from I equals 1 to n of ai closure. So, regardless of which x we choose from the closure of the unions, x will also be contained in the union of the closures. Thus, the union from I equals 1 to n of ai is contained in the union from I equals 1 to n of the ai closures. And hence, we have the union from I equals 1 to n, the ai closure, is actually equal to the union from I equals 1 to n of the closure of ai. Alright. So that finishes part A. Now we move on to part B. Okay, so for part B, we want to prove inclusion in one direction for infinite unions. And so in the proof above, I sort of I started with the easy direction. The first direction was the easy direction, and the second direction was the harder direction. And so basically, this proof is actually nearly identical to the proof of the first part of A. And so, how should I do this? Let's actually just... Here, do you know what I'm going to do? I'm going to take this, and assuming that this doesn't entirely break my computer, I'm going to just copy and paste this, and take some of the n's and replace them. Oh no. Guess I have to go fast. I gotta sonic this, because otherwise my computer will just not cooperate with it. Okay. Okay, so let's see if I'm able to paste this entire thing here. Yes. Okay, don't die on me. Almost there, almost there, almost there. Yes. Okay, cool. So here's what we're going to do. This is nearly identical to the proof of the first part of A. So let A prime be the set of limit points of A. What we want to prove is that the union of... We want to prove that the infinite union of the closures is contained in the closure of the infinite union. Okay, so first, we'll take X to be an element of the infinite union of the closures. Then there still is some J such that X is contained in the closure of AJ. And if X is in AJ, then X is contained in AJ, which is contained in the infinite union of the AIs, which is contained in the closure of the infinite union. If X is a limit point of AJ rather than necessarily in AJ, then there exists a sequence. We'll use M here again just to not confuse with the N that we're already using. There is a sequence of points in AJ not equal to X such that the sequence converges to X. So then this sequence is contained in AJ, and since it's AJ set minus X, and since it's in AJ, it's in the union, the infinite union of the AIs. And this implies that X is in the... Since the sequence is in the infinite union and converges to X, it means that X is a limit point of the infinite union. And hence, the infinite union of the closures of the AIs is contained in the closure of the infinite unions. Okay, and that finishes part B. Now part C. My computer's starting to run slow. I really hope that I'm able to draw this picture and everything be included. So, how should we go about part C? Well, if we think about what could possibly go wrong in part A? In part A, when we were doing the other direction, what did we use? Well, we broke it up into those IJs that we had, where IJ was the set of indices which are contained in AJ. And what we used was the fact that we had just a finite collection of IJs, and thus by the pigeonhole principle, one of those IJs must contain infinitely many elements. That was sort of the key to that proof. And we needed to use that in order to finish the exercise. So the natural thing to think here would that be okay, well, if we want an example where that inclusion does not hold for infinite cases, we should probably look for a case, or we necessarily must look for a case in which you have this sequence of AIs that you're taking the union of. You want a case in which you have this sequence where you have a converging sequence, but no AI contains infinitely many terms of this sequence. And so sort of the natural thing to think of, what sort of sequences have we worked with before? We've worked with that sequence of elements of the form 1 over n. Let's see if we can try to make something work with that. So for I and n, the natural numbers, let xi be simply 1 over I. Let delta I be... What we want to do is we want to take we want to find a radius of a, we want to take each xi and put it in a ball that will not contain any other xi's. And so the only way to guarantee that, well, you got to make the radius small enough. And we know xi, if you start to like go out from there, the first elements of the sequence that you'll run into are xi plus 1 or xi minus 1. And because of the properties of the function 1 over x, you know that the distance between 1 over I and 1 over I plus 1 will be smaller than the distance between 1 over I and 1 over I minus 1. And so what we want to do is we want to take that shorter distance and cut it in half. So delta I is going to be the distance between xi and xi plus 1, which since xi is greater will be xi minus xi plus 1. This will give us a positive number. We divide by 2. And finally, we're going to let ai be the interval of radius delta I centered at xi. So what does this look like? And this is really, again, what I really like about this type of analysis is that you can draw pictures. So we go from 0 to 1. I should make this a little closer. Say here. Now this will be 1/2. This will be 1/4. This will be 1/8. What else do we have in here? We've got a third is maybe somewhere around here. A fifth is, oh man, I don't know. Let's just put dots here. There's going to be a whole bunch of other things here, but I don't know how small I need to draw them. Okay, so what does A1 look like? A1, well, x1 is 1 and x2 is 1/2. So A1 is going to be the 1 minus 1/2 over 2 is going to be 1/4. So A1 is the ball of radius 1/4 centered at 1. So if we go from 1 to 1/2, then 1/4 is this distance. Okay, so this interval here, this is A1. Now for 1/2 to 1/3, just eyeballing this distance and cutting it in half here, we get this, and so this is what A2 is going to look like. Ball of radius delta 2 centered at 1/2. And delta 2 is half the distance between 1/2 and 1/3. Then of course here, this will be A3, and then A4 will probably look like something like this. Blah, blah, blah. And so on and so forth. And so you've got these intervals that are in decreasing and decreasing length that just keep shrinking. Okay, and just as a lot of the properties that we've talked about with the sequence of 1 over n has to do with the fact that it has a limit point at 0, we want to use that to our advantage in this example too. Okay, so note that 0 is a limit point of the union from I equals 1 to infinity of AI, the closure of the unions, and this is because the sequence xn is contained in this infinite union, because again, each xi is the center of the interval ai. And so certainly the sequence is contained in this, certainly the sequence is entirely contained in this union, and it does not include the point 0 because no point in the sequence is ever 0. And as we've already proven in previous exercises, or as you can prove for yourself, the xn's go to 0. Converges to 0. Okay, so 0 is in the closure of the union. However, for each I, the distance between the origin, 0, and the set AI, well, what is this going to be? It's going to be the distance between 0 and the leftmost point on the interval. And so, let's see here. So it's centered at xi, and it has radius xi minus xi plus 1 over 2. So the distance is going to be xi minus delta I, which is xi. And, well, I could write it out more, but all we care about is that this is strictly greater than 0. And so 0 cannot be in the closure of AI, because certainly 0 is not in AI, and for 0 to, the fact that the distance between 0 and AI is strictly greater than 0, then again, I don't know if the notation of distance between a point and a set has been rigorously proven at this point. I think it's a later exercise, but in any case, you can see what, if you just take the fact that xi minus delta I is strictly greater than 0, the distance between the point 0 and the point xi minus delta I is strictly positive. What that means is that you can surround the point 0 in a neighborhood, say, you take the neighborhood centered at 0 of radius xi minus delta I over 2. Then that neighborhood will not contain any elements of AI closure, because what you'd have is you'd have 0 here, and you'd have xi, then AI would look like this, and then you're taking the distance between 0 and this point here, and you're cutting it in half, and you're making a neighborhood like this. And this is going to be our neighborhood n. And so this is a neighborhood of the origin, which clearly, because there's a positive distance between n and AI, and this neighborhood n therefore does not contain any points of AI, and therefore 0 cannot be a limit point of AI. So therefore 0 is not in AI and it's not a limit point, which means that 0 is not in the closure of AI. Thus, in this case, 0 is certainly not in the union from I equals 1 to infinity of AI closure, because in order for 0 to be in the union of the closures, it has to be contained in at least one of those sets. There needs to be at least some j such that 0 is contained in the closure of AJ. But that doesn't hold for any j. So we found an element 0, which is contained in the closure of the unions, but which is not contained in the union of the closures. Therefore, we have constructed an example in which the union of the closures is a proper subset of the closure of the unions, because we found something in the later set which is not in the former set. And that's what we were looking for, and so this completes the proof.